I just want to also note two special cases of what we have discussed. Namely, if you take the field K is Z mod P, then we have said that every element alpha in Z mod P power P minus 1th power equal to 1. That is because this alpha is in the alpha non-zero. Alpha is in the group ZP cross, this is a group, and this is a group of order of this group is P minus 1, and every element raised to order of the group is identity element in that group. This is Lagrange theorem. Theorem for groups. Therefore, every element alpha is a 0 of this polynomial x power p minus x. So, V ZP, I already mentioned this, but let me write once more. This is all ZP. In particular, if I look at this polynomial x power p minus 1, this I can factorize into linear factors over Z mod P. That is, this will be the product x minus k, k varies from 1 to p minus 1. Here these k's I am identifying with their equivalence classes, the residue classes mod P. So, in this is a polynomial identity with coefficients in the field Z mod P. In this, if I substitute x equal to 0, what do I get? I get minus 1 because this is 0 equal to this is 0 and product minus k so many times. So, minus 1 times minus 2 go on till minus p minus 1, and this is congruent to modulo congruent, this equality is a congruent modulo p. Mod p. This is something famous. So, this minus 1 coming how many times? Even number of times, because p is prime, note p was prime number. So, this is same as minus 1 is congruent to p minus 1 factorial modulo p. This is called, you remember, this is called Wilson's formula. So, which we have proved it on the by using the polynomial identities. Okay. The next one I want to mention, which also we will need more often. This is a theorem on identity theorem for polynomials. Very useful for many calculations, in particularly for interpolations. So, let f and g be two polynomials of degree f and degree g, both are less equal to n. We want to know how do we infer that f equal to g, the conditions to conclude f equal to g, equality of g. So, the condition is, suppose there exist n plus 1 different elements T1 to Tn plus 1 in K, distinct elements in the field, such that when I evaluated at f at Ti and evaluated g at Ti, and if these are equal for all I from 1 to n plus 1, then already the polynomials are equal, then f equal to g. Proof. Just look at the difference polynomial f minus g. The degree of this difference cannot exceed n, because both are of degree less equal to n. So, difference will be not more than degree n. But this polynomial f minus g, all these points T1 to Tn plus 1, these are distinct, and the assumption the values are equal says that they are zeros of f minus g. And we know a polynomial of some degree can have at most those many different zeros. Therefore, the only possibility is f equal to g. So, I will write the reason here, since for the number of distinct zeros of any polynomial is bounded by its degree f. For any polynomial f, the number of distinct zeros of any polynomial f is less equal to the degree f. Here the degree could be even smaller than n, and there are at least n plus 1 distinct zeros. So, degree, so this is very simple. So, in particular when your field is infinite, then so in particular what is the immediate consequence of this? So, in particular if k is infinite, then distinct polynomials define distinct polynomial functions. Let me write in the notation for a clearer understanding. This means the following. See, we have the set of polynomials here and we have the set of functions, and we have a natural map here. The map is, take any f, this is a map I denote by epsilon. F goes to, it should go to a function k to k. This is the function, a goes to f of a. So, polynomial has mapped to function, this is a polynomial function. The image of epsilon is precisely the set of polynomial functions. With values in k actually, in k. So, this is a subset of this k power k. What we have proved here is, if k is infinite, then this map epsilon is injective. If I have two different polynomials, then their images as functions are different. That is because if they are equal, then their functions are equal, then they will be equal at infinitely many points. In particular, they will be equal at more than the degree points, and therefore, by earlier remark, they will be equal. Now, it is very interesting to find what is this image set in general. I will just now give only one more remark, that too without proof. If k is finite, this will be written more in supplement. If k is finite, then actually epsilon is surjective. That means any polynomial function, any function is coming from a polynomial function. It is defined by a polynomial function. So, this means, so that is every function from k to k is a polynomial function. Just one example, just to digress. So, let us take now, do not take k finite and see what happens to this surjectivity. If k is c, complex numbers, and suppose I take a function and phi is a function from c to c. So, defined by, say on the disk, this is, think of complex numbers as this complex plane. On the disk, on this you define it to be 0 function, and everywhere else you define it to be the value 1. So, formally writing is phi of z is 0 if mod of z is less equal to 1 and equal to 1 otherwise. So, you get a function from c to c. This function cannot be a polynomial function. This function phi cannot be a polynomial function. That is, the function phi does not belong to the image of epsilon. Image of epsilon is precisely the polynomial functions. Why that? Because you see the whole disk is mapped to 0. A disk has infinitely many complex numbers. So, if it were a polynomial function, it will vanish only at infinitely many points. But this function vanishes in fact countably many or uncountably many points. So, this cannot be polynomial function. Okay. I want to end this by giving only one definition. So, this also will be very convenient to use this terminology later. A field K is called algebraically closed if every non-constant polynomial f in Kx has a 0 in K. Once it has 1 0, then you can repeat the argument and every polynomial all the zeros will be in K. This is, for example, theorem of Gauss D'Alembert says C is algebraically close. This is D'Alembert Gauss. Incidentally, D'Alembert wanted to prove this theorem because he wanted to solve differential equations. This I will do it in when we do solutions of the differential equations. And the field R, Q, finite fields are not algebraically close. So, proving theorems in linear algebra over C will be easier for this reason, because C is algebraically close, and because the other fields are not algebraically close, the proving theorems about eigenvalues etc., they will be more difficult to prove, but similar techniques work for arbitrary fields. Okay. Now, I want to continue next example. Also I have to finish this, so I have to also digress about example 5, I think, rational functions. I will be more briefer in this. So, the first one is I just want to define. So, rational functions are like rational numbers, that is why the name rationals, and still one should not call function, one should actually call rational polynomials. But in the literature they are referred as rational functions. So, I will keep using, but I will warn you when some things are necessary. So, what are rational functions? They are polynomials by one polynomial by another polynomial, like a fraction, one integer divided by another integer. So, f and g are two polynomials over a field in one variable, and g should be a non-zero polynomial. And obviously, you know, you extend the definition of sum of polynomials by usual fraction rule, clearing the denominators, like what you have done it for the rational numbers. And also similarly, you can multiply them. So, this is multiplication of rational polynomials. So, already with this, the set of all rational functions are denoted by k round bracket x. This is the set of all rational functions. And one of the aim in this example, I want to show you this is a vector space and I want to find a basis for this vector space. This is the aim of this. So, I am digressing which will lead us to finding a basis, and that is very, very important, because especially if you remember how you have integrated the functions, integrated rational functions. There you have used a technique called partial fractions, and so I am recalling those things in a brief way, but more or less self-contained. So, obviously all polynomials are rational functions, and we have extended the definition of sum of polynomials and product of polynomials to the rational functions. So, that means we have extended this ring, this kx is extended to this bigger ring. So, the binary operations are in the polynomial ring are the restrictions of the binary operations from the bigger set. So, that means this kx is a subring of rational functions. This is also ring. Okay, rational functions with addition and multiplication is obviously a commutative ring. The same similar way you can, what we have done for a polynomial, you can check, this is a formal checking. Actually it is better, because any rational function, if it is a non-zero rational function, non-zero simply means f is non-zero. Obviously in the definition g has to be non-zero, but a rational function is 0 if and only if the numerator polynomial is non-zero. So this means I can invert it. So that means this f over g, if it is non-zero rational functions, then g over f also makes sense, and that is also rational function, and this is the inverse of f over g in this ring. This is the inverse. So that means we have checked that this set of rational functions k round bracket x is actually a field. That is the reason sometimes it is called the field of rational functions. In one variable over k. So this is, now we have added one more field in our list. How do you construct a bigger field from a given field? Okay. So now okay, the most important tool used in the calculation or in computation of rational functions is of course division with remainder. Remember we have divided, if you have two polynomials f and g, and if g were non-zero, then we have divided f by g and written a quotient and remainder. So that means we have written f as q times g plus r, where q and r are polynomials again, uniquely determined, with the property that either r is 0 or degree of r is smaller than degree of g. So the same thing now I can use it rational functions, and same equation I rewrite is f by g equal to q plus r by g. I just divided both sides by g. So if I want to study these rational functions f by g, this is a polynomial, q is a polynomial. So I might concentrate on the r by g. So to study f by g, we may assume degree of numerator f is strictly smaller than degree of the denominator g, because I will forget this, and q is a polynomial. So we know how to study polynomials better than rational functions. So I will just concentrate on this part, and this part has numerator is degree, either it is 0, so it is a rational function 0. In that case we stop, because we know we have to study only polynomial, otherwise we can assume this. Okay. I forgot to mention that these rational functions also has a scalar multiplication. This has also scalar multiplication of k. and again the ring structure and this scalar multiplication are compatible, because that was we have checked that in polynomial case, and the same checking will also check that this is compatible with the ring structure of the field of rational functions. So, that means this field is a K vector space and also commutative ring. And these structures are compatible. So, that means K rational function field is also K algebra. Remember, K algebra means vector space and commutative ring, and both these structures are compatible. And this the polynomial algebra, this K algebra Kx polynomial algebra is a K subalgebra of and by the earlier results and remarks, we know that the elements in this polynomial algebra are studied better. And now I want to, here we have a basis. The basis here was, you remember, 1 x powers of x. This is a basis, but here we need more. Remember, 1 over x is never a polynomial. 1 over x, this is a rational function, this is in K round bracket x, but 1 over x can never be a polynomial. 1 over x cannot be invertible in the polynomial ring, because you see, if there is a polynomial who is the inverse of this, then you can write it 1 over x times f equal to 1, and then shift this x to the other side, then you will get this is equivalent to saying f equal to x. But still, what is the contradiction? So, check that this is not possible. X cannot have inverse, because inverses, we have noted, inverses have only degree, possible degrees are 0 because of the degree formula, and this degree is 1. So, this cannot have inverse. Okay. So, f will not be polynomial. In f will not be polynomial, but it is a rational function. So, in the rational function something better happens. Now, polynomials become invertible there. So, it becomes a field in a smallest possible way. So, this means this polynomial ring you have embedded in a smallest possible way to this bigger field of rational functions. This is also sometimes called the quotient field of Kx, is also called quotient field of Kx. More on this usually one studies in a course on algebra or algebraic geometry and things like that. So, I will not get more into details in this, but I will do it only what we need in a linear algebra course. Okay, so remember our aim is to find a basis of the K vector space Kx, K round bracket x is a field of rational functions, and we are going to repeatedly use the fact that we will repeatedly make use of the fact that division with remainder. Okay. So, I want to talk about first a case where the denominator polynomial splits into linear factors. So, I want to recall what is a partial fraction decomposition. I want to recall this. I will write down the precise statement, but I do not know whether I will provide a proof in this course, or definitely they will be, the proof will be in the notes. And especially this is more interesting when the field is either, this is the notation I will keep using, this is either a field of real numbers or the field of complex numbers. In this case it is more important. So, let me stick to that case. So, k is kx, k is the double line k, that means it is either a field of real numbers or the field of complex numbers. And let us take two polynomials f and g in kx, and I will also assume that the degree of f is smaller than degree of g. And I will also assume to start with the field is C, or I will want to assume that G is a product of linear polynomials. So, G factors like this, G is x minus alpha 1 power n1 and x minus alpha r power nr. This happens for any polynomial in C, that is what we have seen in the earlier part of the lecture. In this case, how can you write f by g? That is the question. F by g can be written. So, this can be written in the form alpha 1 1 divided by x minus alpha 1 plus alpha 1 2 divided by x minus alpha 2 square, go on till you achieve the full power, that is alpha 1 n 1 x minus alpha 1 power n 1, and then start with the next 0. This is done for the this factor. Then alpha 2 1 divided by x minus alpha 2 plus alpha 2 2 x minus alpha 2 power 2. This is not alpha 2, this is alpha 1. So on, go on till alpha 2 n 2 x minus alpha 2 n 2, and keep doing this. The last one will be alpha r 1 x minus alpha r plus alpha r 2 x minus alpha r square plus alpha r n r x minus alpha r power n r, where this alpha I k they are constants. This for a fixed I, this k varies from 1 to n I, and they are uniquely determined. I want to prove this. So, right now we assume this, and let me conclude what we have proved then. So, what is it useful for? So, this means okay. So, what I want to claim is if I take the powers of x, k is varying from where 0 to everywhere, right. So, better to write k is in n, and then take such things 1 over x minus a power m. Now, what is varying? A is varying as a constant and this M varying as a natural number. So what we have checked, that is, if you take this big set, this is a k basis of kx, because let us go back and show you. So here if you have a, so what does it mean that you want to show it is a basis? That means we want to show that any rational function is a finite linear combination of these cases, right. So that is any f over g where f and arbitrary polynomials, g non-zero, this should be this is a linear k linear combination of this rational function, these rational functions, these special rational functions. These means powers of x and this simple rational function. This is 1 over x minus a power m. A is varying, m is varying. So how do you do this? First of all, you use division algorithm to assume that f over g has a property that the degree of the numerator is smaller than degree of g. How did we achieve that? See, if you go back, see here we have taken the division algorithm and look at f by g and then you get a polynomial, but polynomial here is a finite sum of the x powers in a unique way. So this part we have managed. Now we have to manage this part r over g, but therefore we have an extra assumption that degree of the numerator is smaller than degree of the denominator. And now remember that I am assuming k is c in this. This is very important. So I should write here this double k, right. Once you have assumed that, then the denominator polynomial will split into linear factors. Because of that assumption, I can assume g factors like this. And I can also absorb the, if g has the top degree coefficients of non-zero constant, that is in a field. So I could have absorbed that in a big numerator by multiplying by inverse. So without loss I can assume g is like this. And in that case, what is our partial fraction decomposition says that f by g looks like this. But you see, this is a coefficient of 1 over x minus alpha 1. This is a coefficient of 1 over x minus alpha 1 power 2 and so on. So what this partial fraction decomposition precisely means that this rational function can be written as a finite k linear combination of these special rational functions. So therefore it is a basis, and now you see this basis is bigger. So this in, and also it is nice because this was the basis of the polynomial ring and this we have extended to a basis. So I think I think I will stop here and we will continue next time. Thank you.